Good morning, everyone. We continue today with our topic. We will continue with the capacitors. Three types of capacitors. We will be looking at the parallel plate capacitor, the coaxial type capacitor, which is a cylindrical based, and spherical capacitor. Now, let's start with the parallel plate capacitor, where we have seen before that the parallel plate capacitor is made of two uh, overlapping electrodes with an insulator in between. Every electrode has a charge. One of them is positive charge, and the other one is a negative charge. If you are to calculate the charge density, then we have here the sigma equals to Q divided by A, where A is the overlap area for this capacitor. Now, in order to extract the potential difference for an ideal capacitor, we will ignore the fringing field at the side. Those ones, we will ignore those fringing field. We will assume that it is an ideal capacitor. In this case, if we are to derive the potential difference between the two electrodes of the capacitor, then we will first of all orient the bottom plate with negative charges, and then, for example, the top plate here with the positive charges. Now we have the electric field, as you can see, pointing downward. In this case, the electric field, based on the two sheets of infinite sheet with the charges, if you recall, we have said that the electric field inside is uniform and equals to sigma divided by epsilon. Now, for the case of the top plate to be a positive, then the electric field is pointing downward, and based on this x-axis pointing upward, then it makes sense that the electric field as a vector will be minus q divided by epsilon a I, and I is the unit vector for the x-axis. Now, in order to derive the potential difference, we will do the integration here from the negative plate toward the positive plate minus. So minus, we will integrate from the negative plate toward the positive plate for the dot product of the electric field and the differential element. So in this case, the electric field is uniform. As we can see here, we substituted the electric field. Let's work on this. So we have here the positive, as we said, that the positive plate here, we put it at the top, negative, and then this is the x-axis. We know that the electric field is pointing downward this way. So this is the electric field, and this is the distance d, starting from 0 to d. Now we will integrate, if we take this one as plate 2, this is 1. The potential difference equals to minus integration from the negative toward the positive. So from 2 toward 1 for the electric field dot the differential vector element dl, and as you can see here, dl as a vector is dx I hat, and the electric field, as we said earlier, is minus sigma divided by epsilon, also I hat. So if I am now to calculate the potential difference, it will be from x equals 0 to x equals d for electric field as minus sigma divided by epsilon I hat dot dx I hat, and this is going to be delta V as minus with a minus will go, sigma and epsilon will go outside. I ended up with dx, and integrating dx is going to give me x from 0 to d, and in this case delta v equals to sigma d divided by epsilon, or I can say that the potential difference delta v equals to, if I substitute sigma with the q divided by a, d over epsilon a. So now this is the potential difference between the two parallel plate capacitor. Now if I want to calculate the capacitance, then the capacitance, we know the capacitance Q equals to C delta V, as we have seen earlier. Then in this case, C as Q divided by the potential difference, or C equals to Q divided by Q D over epsilon A. Q will cancel, and now the ideal capacitance for parallel plate will be epsilon A over D, and this is the ideal equation where this epsilon equals to K epsilon naught. So we need not to forget that epsilon equals to K epsilon naught, where K is the dielectric constant for the insulator. So this is the potential difference and capacitance for a parallel plate. We just derive them. Then we have the energy stored in the electrostatic field, WE, as the half the volume integral of the epsilon E squared dV. Uh, at the end, this energy is basically calculated by taking out the electric field because it's uniform, uh, the volume, which is A times D, then I can substitute D over epsilon A with V over Q, simplify it to get the energy stored in the capacitor to be half QV, or if you substitute Q with its equivalent, you can get the energy as half C potential difference squared. So it's half QV, or half C potential difference squared. The second type is the cylindrical type, which is the called a coaxial cylindrical conductor. In this case, we have an inner conductor that has a radius of RA, and we have an outer conductor that has a radius of RB. So the electric field, as you can see, is in between those two conductors. Electric field is not uniform here. However, it is constant in magnitude at the same radial distance. So we have the positive charge distributed on the surface of the inner conductor, and we have a negative charge distributed on the surface of the outer conductor. The coaxial length here is L. So if we want to extract the potential difference between those two conductors, again, we can do exactly what we have done for the parallel plate capacitor. We know the electric field that we have derived earlier from Gauss's law to be given as E equals to Q divided by 2 pi epsilon RL R hat. This is the electric field that we have calculated from Gauss's law from a previous lecture. So what we need to do here is to derive this potential difference. It's going to be again straightforward. We have we have two concentric cylinders. This is the inner one with an Ra. We have the positive charge on the inner one. This is the outer one, Rb. We have the negative charge. This is the length. This is the electric field. Electric field is pointing in this direction. So we have seen that the electric field, we've derived it earlier, equals to Q over 2 pi epsilon R L, and here the unit vector is R hat. We have derived that before earlier. Now we need to calculate the potential difference between those two conductors. So how do we do this? We know that the potential difference V equals to minus from RV, which is the negative of the electric field potential, to RV for E dot dl. Now, if we want to know how did we get this one from, remember we said that the potential uh, electric potential energy difference equals to that we have said before equals to the work, right? And we said that usually when we have the electric field as non-uniform, we use the integration. So we will be integrating here from A to B for the F dl, and we know that the potential difference here is a Q delta V. So when we divide it by Q, we got delta V equals to minus 1 over Q, and this F is indeed QE. So in this case, we got rid of the Q and we came up with this expression. Now let's continue. Here we have the potential difference delta V equals to minus, again we said from RB to RA for the electric field, which is Q divided by 2 pi epsilon RL R hat, and we have the delta E in this case is along the radial axis, which is dot dr R hat. So this is going to result into the potential difference delta V equals to R hat dot R hat. Then I can take the Q to pi epsilon L. All those are constants. I can take them outside and I will end up with RB to RA for dr over R. And in this case, this integration is going to give me minus Q over 2 pi epsilon L natural logarithm of R RB to RA. Then potential difference is minus Q over 2 pi epsilon L logarithm RA minus natural logarithm of RB. Then if I take the minus inside, then this becomes Q over 2 pi epsilon L logarithm RV minus logarithm RA. And then we know that logarithm x minus logarithm y equals to logarithm x divided by y. Then this potential difference becomes q over 2 pi epsilon L logarithm RB divided by RA. So this is the potential difference between two cylindrical, concentric cylindrical conductors. Now, if I want to calculate the capacitance, then I know that Q equals to C delta V, then C equals to Q divided by delta V. I know the potential difference. Then C is Q divided by Q over 2 pi epsilon L RV over RA. In this case, C becomes Q is going to cancel 2 pi epsilon L, and this is over logarithm RV by RA divided by RA. So this is the capacitance for coaxial capacitor that is of cylindrical shape. Okay, so we've derived this. Now let's move on to the spherical, the concentric conducting spheres. For the concentric conducting sphere, we're not going to derive the potential difference and the capacitance. We will be using those two expressions. Okay, so this is the summary of the capacitances that we have derived today. One for the parallel plate, and this is for the cylindrical coaxial cylinder capacitor, and this one is for the concentric sphere capacitor. In the concentric sphere capacitance, as you can see here, we have the outer conductor and we have the inner conductor, and there's an insulator in between. Now, after we derived the capacitances for those shapes that we have seen, now we can go to the circuit level and talk about some simplifications for some configurations that we can see in the circuits when we hook up a few capacitors together. So the first combination is when those capacitors are in series, for example, when those capacitors are connected in series this way. If I have uh, C1 that is connected in series, C2, C3, for example, then in this case, those capacitors will not be added. The inverse of those of the equivalent capacitance so will be added. So I will be 1 over C equivalent becomes 1 over C1 plus 1 over C2 plus 1 over C3. So this is the equivalent of the, so C, one of the C equivalent is the inverses of the capacitances. So this is for the series. If I have capacitors that are in parallel, where those capacitors are connected in parallel, for example, the word parallel and series, the word parallel means that both electrodes are connected together. One electrode from one side, the second electrode from the other side. So in this case, I have C1, C2, and C3 are connected in parallel. And in this case, the C equivalent would be the summation of those capacitors. So when they are connected in parallel, I add those capacitors. Now let's look at this example. Here we have this configuration of capacitors that are, I can see, connected, some of them in parallel, and also there are some series connections as well. So in this case, I have the 12 and the 6 microfarads connected in series. If I am to calculate the equivalent capacitance for 6 and 12, then it will be 1 over C equivalent 1 equals to 1 over 6 plus 1 over 12. Always remember the units. So here C equivalent 1, because of those two are only two components. It can be calculated by 6 times 12 divided by 6 plus 12. This applies only to two capacitors connected in series. So we have 6 times 12 divided by 18, and the result will be 4 microfarads. So we have 4 here microfarads. And then this 4 microfarads is connected in parallel now with the 11 and with the 13. So we have a total of 18. So now those are going to give me now C equivalent 2. And now C equivalent 2 is 4 plus 11 plus 3. And C equivalent 2 is 18 microfarads, right? Now I have this C equivalent to connected now in series with the 9 microfarads here. C equivalent to is in series with the 9 microfarads. So in this case, I will 18 times 9 divided by, the answer is, this is C equivalent 3. C equivalent 3 is 18 times 9 divided by 18 plus 9, and the answer was 6 microfarads. So C equivalent 3, which is the total capacitance, is 6 microfarads. Let's move to the next question here. In this question, we have the following: two capacitors that are connected in parallel, as shown here at point uh, C and D. Now, C and D are the same as A and B. We have to be aware of this. That this whole wire will have the same potential everywhere. So I have A is the same as C and B is the same as D. So here, this is a 2 microfarad capacitor, and this microfarad capacitor was replaced with a 4 microfarad. Now the question is asking, what's going to happen to the potential difference across this capacitor and the capacitance? So the first option is, if I replace 2 microfarads with 4 microfarads, the potential difference is going to increase across the capacitor by a factor of 2, because this is 4 and this is 2. So the ratio between them is a factor of 2. So the first option A is delta VCD is going to increase. The potential difference is going to increase by a factor of 2. And but the charge on the capacitor between C and D stays the same. This is option number 1. Of course, the potential difference is not going to increase. The potential difference is defined by this battery. So the potential difference here is not going to increase, which basically put this one as wrong. So B, the potential difference CD decreases by a factor of 2. Again, this is wrong. The potential difference is not going to decrease. The potential difference is defined by the battery here that is connected directly. So this capacitor is connected directly to the battery. So the potential difference across the capacitor will be the same as the potential difference across both capacitors actually. So A and B are wrong. The charge on the capacitor between C and D in C increases by a factor of 2, but delta VCD stays the same. Well, yes, delta VCD stays the same. Now, is the charge going to increase by a factor of 2? We can see that Q equals to C delta V. So if the capacitor has increased, so here we have delta V. Again, we said that the potential difference is going to be the same, not going to change. So delta V equals to Q over C. So if the C increases by a factor of 2, definitely Q will increase also by the factor of 2 because the ratio has to stay the same. And yes, C seems to be the correct answer among those five options here. The charge on the capacitor, now D, charge on the capacitor between C and D decreases. No, it's not going to decrease. It will have to increase in order to maintain the same ratio for the potential difference. Now let's move to the currents. We know that the definition of the current is the time rate of the charges flow. As long as we have charges that are in motion, we do have a current. Currents can be looked at as positive charges flowing in a conductor, for example, or negative charges that are flowing in the opposite direction. Now, uh, the direction of the current has been taken as the direction of the positive charges. So the positive direction for the current is the direction of the positive charges. In both cases, charges are in motion, either positive or negative. So it depends on how you look at it. If you look at it as a positive, you take it as the positive. If you look at it as a negative, it is the opposite direction. However, the positive direction for the current is taken as the positive direction of the charges. The instantaneous current is given as the dq over dt, as we have said earlier. The unit for the current is ampere, which is 1 coulomb per second. Now, if we want to derive this current using uh, the drift velocity and also the number of the carrier density in the volume, that it will be derived as the following. We have the current equals to N, which is the number of the charges density in the volume. So that's the density of the carriers times the volume. It's going to give me the amount of the charges within this volume times the charge will give me the total charge within that volume divided by delta t. So those are the charges that are in motion. Number one, we have the density of the number of those charges. If we multiply it by the volume, we get the total number of charges. If we multiply it by the charge, we get the total charge, and then this is during this time. Now, if we are to look at this volume, this is the volume that we are interested to use, and this volume has thickness of delta x and the cross section of A. So if I substitute this volume with A times delta x, and then this delta x as the drift velocity times the time. So delta x here equals to the drift velocity times the delta t. Then if I substitute this one here and I substitute the volume in here, I will get this equation, which is basically the current equals to N, which is the number of the carrier density in volume, times the charge, times the drift velocity, times the cross section of the wire, and this is the current, as I said, given in the drift velocity. Now, if you want to calculate the current density, then you have to divide by the cross section of the wire. This way, you have the current density of the charges flowing in this conductor. So this will be I divided by A, and in this case, it will be NQVD. So it will be N times Q times the drift velocity. Now let's look at this question. In this question, uh, when the current through a wire is increased due to an increased voltage. Now we all know that the potential difference across the wire caused by the battery, for example, is the one that is inducing force causing those charges to flow. So now those charges that are flowing, if the potential difference, the voltage has increased, which of the following quantities change? Does the density of the charges increase per volume, or the drift velocity increases, or both, or either can but both don't necessarily have to, or don't know what the question is asking? So in this case, if the potential difference increases, in this case, what we can see that if potential difference increases, this means the current will increase, and if the current increases, the only parameter that can increase is the drift velocity. The cross section is constant, the charge is constant, and the density of the charges is also constant. So in this case, the answer to this question would be the answer B.